Okay, in this video, we're going to introduce the most basic ideas of integral vector calculus. So we are going to imagine that we have got two vector fields. The first one is f. It's a function of parameter t. The second vector field is g, is also a parameter of t. So given that f and t are vector fields, then if so that's the first thing. Suppose those two are vector fields. Also, suppose the derivative of g with respect to t is equal to f. Then the integral of f with respect to t is going to be g, but this is going to be plus a constant. Let's call it k, and so this is the indefinite integral. So it's kind of similar to what happens with scalar functions. So that is going to be the indefinite integral of f of t, right? There, and then also so let's say moreover the integral of f from t equal to alpha to t equal to beta is going to be the vector g evaluated between alpha and beta, and this is going to be g of beta minus g of alpha. Again, this is the same idea as we've seen with scalar functions, and this now is the definite integral. Just going to look at an example or two to demonstrate what we are talking about here. All right, so in this example, we have a particle whose acceleration is given by this vector here, 12 cosine 2ti minus 8 sine 2tj plus 16tk, where t is greater or equal to 0. And then we're told that the particle is initially at rest at the origin, and then we want to find the velocity v and the position r at any time t. So we're going to start by mentioning that the relationship between the displacement and velocity is that the derivative of the displacement is going to be equal to the velocity in kinematics, and the acceleration is the derivative of the velocity, or the second order derivative of the displacement vector. What this means is that the velocity is therefore going to be the integral of the acceleration vector. So in order for us to find the velocity here, so we are going to need to integrate the acceleration vector, which is 12 cosine 2ti minus 8 sine 2tj plus 16tk. So this is going to be an indefinite integral. So let's work through that. So the integral of cos 2t is going to be negative half of sine 2t. So that means this is just one moment. No, it's actually not negative, it's positive. So the first term is going to be 6 sine 2t, and then the integral of negative sine is just going to be positive cosine, but we're going to have to divide by 2. So this is the I component. So here 4 cosine 2tj, and then 16t integral of that is going to be 8t squared. This is the k component, and then this is going to be plus some constant, but this constant is a vector because we're integrating a vector. Now we are told that at time t equal to 0, the velocity is 0. So that means if we plug in t equal to 0 here, we must get the 0 vector. So on the left hand side we have got velocity here, so that should be 0. So that means 0I plus 0j plus 0k, so that's the 0 vector. And then if we plug in 0, this x component is going to be 0. This y component is going to be 4. So we're going to have 4j. And the z component, which is this one, is going to be 0 as well. So this is telling us that lambda is actually going to be minus 4j. And so we can now plug this back in here. So we're going to have RV being equal to 6 sine 2ti plus 4 cosine 2tj plus 8 t squared k, and then this is going to be minus 4j. And then if we collect terms, it's going to be sine 2ti, and then we're going to combine these two terms here. So we can write this as 4 cosine 2t minus 4j, and then we have got 8t squared k. So this is going to be our expression for the velocity. And then now we can find the expression for the displacement or position by integrating this. So the position vector r, or the displacement, is simply going to be the integral of the velocity vector, which is this one here. So integral of this term is going to be negative 3 cosine 2t, because we're dividing by the 2. And then integral of this term here is going to be 2 sine 2t. Integral of minus 4 is just going to be minus 4t. and then plus integral of 8t squared, going to be 8 over 3t cubed k, and then this is going to be plus some other constant, let's call it gamma. Now again, we're going to have to evaluate this. Remember that at time t equal to 0, the particle is at the origin, so that means that t equals to 0, the displacement is 0, 0, 0. So if we plug in t equal to 0 here, we must get 0i plus 0j plus 0k. So that is the left hand side. On the right hand side, we will have minus 3i. The j component is going to disappear. This component is also going to disappear, and so we're just going to have gamma there. So this is telling us that the constant gamma is simply 3i. So then we're going to take this and plug it in there. If we do that and tidy up terms, then we are going to find that the displacement vector is 3 into 1 minus cosine 2ti plus 2 sine 2t minus 4tj plus 8 over 3t cubed. Okay, where the 3i, this 3i here has been incorporated into this term there. All right, we're now going to give you a chance to work through a similar example. All right, in this example, we have a particle that has got acceleration given by the vector 2 minus t e to the minus ti plus 12 cosine 2tk for time t bigger than 0. The initial velocity is given by 4j. The initial displacement is given by I minus 2k. So again, want to find an expression for v, an expression for r. So I think you might want to just pause the video and then have a go at this, and then when you continue the video, then you can compare with our solution. Okay, we're now going to scroll down to our solution for number 2. So the velocity we find by integrating the acceleration vector. This term here we integrate using tabular integration. We're going to put a link right here if you're not familiar with this method, so that you can benefit and get the basics of it. But basically, so the integral of this term is going to work out to t minus 2 plus 1 e to the minus t. Then, which is just t minus 1 e to the minus t. At t equals to 0, we are told that the initial velocity is 4j. So if we plug in t equals to 0 here, we get minus I. So that means lambda, this constant of integration, is going to be I plus 4j. If you incorporate this into this, that's going to give us this expression as our velocity. Then to find the position vector, we integrate the velocity, and then again for this term you have to use tabular integration. This works out to this expression here. Then applying the condition at t equals to 0, told that the position vector is I minus 2k. So this gives us the constant alpha to be I plus k. If we incorporate this into R, then this is going to be the final expression for the displacement. All right.